question.
Hello. Okay. Good morning, everyone. Thank you for joining me. Again, my name is Maria, and I'm a grad student at UC Merced. And today I'll be talking about improving the modeling for gravitational lenses used in dark matter inference. So I'll start us off with a little bit of background. And years of studying what makes up the universe has led us to the standard model, which we now believe or realize is really only a very small portion of the total matter in the universe. In fact, most of the stuff in the universe is this thing called that, oh, the wrong one, dark energy right here. But that's not what I'll be talking about today. What I'm focused in is dark matter, which makes up most of the matter in the universe. And there exists multiple, we don't know a lot about dark matter. Things that we do believe we know are that it generates these self-gravitating dark matter structures called dark matter halos. And we also believe that galaxies reside within these dark matter halos. So there exist multiple models that try to describe this dark matter particle. Two of the ones I'm talking about right now will be cold dark matter and warm dark matter. And the main difference between these is the abundance of low mass dark matter halos. So these are two simulations of Milky Way sized galaxies. And if we had our dark matter goggles, this is what we would see. So again, we can't really see dark matter, but you can see that they have a lot more of the small features. So that's plotted here in the halo mass function. So the halo mass function is directly related to the dark matter particle physics. So measuring this halo mass function would allow us to discern between the different competing models. And that's what we're interested in using. So to test for the different dark matter models, I use strong gravitational lensing. To remind us again, strong gravitational lensing falls from Einstein's theory of relativity and is when a bright light source, such as a quasar over here, the light from that source gets bent by a foreground galaxy and it generates multiple images. So us as the observers here can see multiple images of that same source. And the flux ratios or the image brightnesses of those images are used as probes for small scale structure. That's where we could detect possible dark matter features. So we use a method called flux ratio anomaly, and I'll go over what that looks like. So first, we can have a simulated lens observation where all the lensing happens from the one main lens, just as I was describing before. So there's no dark matter here. Now we can see what the effect of one of those dark matter substructures would look like on one of the images. So here I'm placing a dark matter subhalo near that top image, and we can see in the residuals that that image gets magnified. So you can notice the perturbations from that dark matter halo in the image ratios, flux ratios. Now, in reality, we don't just test for one subhalo like that, but we generate realistic populations of dark matter models. So again, we would generate multiple of these and statistically analyze which one would be the most fit for the observation. And using the flux ratio anomaly method, people from my lab, this is Ryan Keeley's work, most recent work, have placed some of the strongest constraints to date on the dark matter particle physics. I'm shouting out some of their work. And this is other examples, but I won't go into detail about this. But yeah, this is using data from JWST, Keck, and HST. Now, what I'm working on is improving the modeling that goes into these gravitational lenses. So I'll start by talking a little bit about the light source that we use. So the light source that I'm interested in is a narrow line region. So the narrow line region is this low density region here. And the light that I'm focused in, again, is the O3. So I use the lines 5007 and 4959, and I'm really interested in this specific region because the narrow line is sensitive to those small scale perturbations. So if there were to be any dark matter halos, we would be able to see them, but it's also resilient to any microlensing by stars. So stars also have mass, but they're not dark matter, not people believe. So we would avoid any sort of flux ratio that would come from the stars. And then the other exciting part is that we can measure those narrow line region flux ratios with the upcoming missions such as Euclid and LSST in hundreds of newly discovered lenses. So using the narrow line region is really important. And then we have used OSIRIS at Keck to measure narrow line region flux ratios. This is an example from B1422. As you can see, we take advantage of the adaptive optics, as we've discussed multiple times before. So big shout out to everyone working in AO. And also, we really care about that spatially resolved spectra. So what I'm looking at, what we're looking, oops, I did it again. we're looking at here is that extracted spectra from the different images. And again, what the light that I'm interested in is that O3, because knowing that the light comes from the O3 means that it's resilient to the microlensing, and that's the signal that I'm looking for. And in previous measurements of these narrow line region lenses, the model to describe the narrow line flux has been a 2D Gaussian. So this really symmetric function, and it works really well for most of the lenses that we have discovered so far. So there's no reason for us to try anything else, except that some of the new lenses that we've discovered actually have an extended emission set in this narrow line region. So to show you, this is that wavelength range over the O3, and you can see that feature if you subtract the continuum light versus the O3 light. That extended feature really comes from the O3, and this tells us that the light source might be a little bit different. So again, our previous model is not good enough. So we want to look for different modes, and observations of realistic narrow line regions at lower redshifts actually indicate that they have more complex structure. So highlighting some of the clumpiness here and some elongated features here. So what I'm interested in is how do these flux ratio measurements get affected when you include a more realistic view of the narrow line region. So I've been working on using realistic, low redshift, and high resolution images to create simulated gravitational lenses and analyze them. So I've chosen a couple of the brightest sources that I could find in publicly available data. This is from the CARS survey, post-ADN reference survey. And my cutoff here is that I want my luminosities to be somewhere around 10 to the 46. So these are really, really, really bright objects. So the reason why I'm choosing this is because most of the quasars that we observe through lensing have similar bolometric luminosities. And I'll briefly go over this is kind of the big chunk of my work. So I've developed two pipelines, one to simulate the lenses and then another one to actually analyze those lenses. So first, I take my real sources. So these are, again, the sources that I've shown you before. I've also done it with other HST data as well, but I found that these are probably a little better. Okay, so then the next step is I lens those sources. So again, I have very low redshift sources, and I pretend that they are at a higher redshift. So I adjust the flux ratios and the flux of the image and what I lens it with a very representative lensing configuration. So my source is directly on top of my deflector. So the mass of the lens is right on top of each other. Then I can create my mock Osiris lenses. And then this is the first part. This is all the simulation component. Then the next step is to actually pretend that I have a real observation and use my mock lenses to analyze them. So this can now be used for any real data that we have incoming. So something like 1413 that I showed earlier. Then I can estimate the different lensing parameters. And then this is the step where I'm actually including my new model. So instead of assuming that the light source is Gaussian, I now can pretend that I don't know anything about it and have a very flexible model to interpolate that source. And then from here, I also can then recover that extended narrow line emission, which is, again, I need to make sure that the light that I'm seeing is light from the narrow line region. And I can extract that spectrum. And then the last thing is to then calculate the flux ratios. So I've done this with a couple of lenses, and I'm showing you here one of the examples. This is 1126. Different sources, and this is one of those lenses. So here I'm only lensing the narrow line region. So in the full pipeline, I do add different point sources and different complexities to really mimic the real observations that we see. But here you're seeing, this is my simulated, oops, wow, how many times? Okay, my simulated lens here, and again, this is all the O3, and then my reconstructed lens here. And then the residuals is essentially 0. So I think my model is doing a really good job at reconstructing this. And then you can really see that in the extractive spectrum. So that is almost identical. And that's really exciting because that means that now I can take in whatever source I want, and I can really recover it no matter whether I know anything about the analytic shape of the light source. So yeah, in conclusion, I've been able to develop this pipeline that simulates and fits these observations of gravitational lenses using those low redshift observations. And coming soon, I'm hoping to measure the real measurements of real narrow line region properties of the lenses that we have, as well as those that will be coming up in other surveys. So yeah, that's all from me today. Thank you.